Dear students, in this lecture now we will discuss about total angular momentum. Here we will discuss about how the magnitude and direction of total angular momentum are quantized. As each electron has some orbital angular momentum which can be represented by L, and electron also has the spin angular momentum, and spin angular momentum can be represented by S. So as both total orbital angular momentum and spin angular momentum both contribute to the total angular momentum, so how we can represent the total angular momentum? Total angular momentum can be represented by J, and it is the combination of L plus S. Here L is the orbital part of angular momentum and S represents the spin angular momentum, and J represents the total angular momentum. As we know that in an atom we have the inner electron and plus valence electron, and we know that about the inner electron, which are also called as the closed shell electron in the closed shell. Why they are called as the closed shell? Because for inner electrons, they have the total angular momentum J and their spin S, both are equals to 0. So that's why these inner shell electron are called as the closed shells, and because their total angular momentum and spins are equal to 0. So the atom has the total angular momentum that is only due to the electrons in the valence shell. So the valence shell electron only contribute to the total angular momentum of electron of an atom, except for the hydrogen atom. As you know that in the case of hydrogen atom we have only one electron, and so its angular momentum is due to its one electron. As we know that the total orbital angular momentum, either it is the total spin angular momentum, both are quantized. Total orbital angular momentum is quantized and spin angular momentum is also quantized. As the total orbital, it has the value L into L plus 1 h curve under root h curve, and spin has the value S into S plus 1 under root h curve, as both has the quantized value. As we know that J which is the sum of L plus S, J like this angular momentum L and S, J is also quantized. So J has the value, J is equals to J into J plus 1 under root h curve. So its value is also quantized, as we know that J is equals to L plus S, as spin can has the value plus half, or either it can has the value minus half. So J can has the value of L plus minus 1 by 2. Let's suppose if we have the condition for the s orbital, as we know that for the s orbital L is equal to 0. When L is equal to 0, then J has only single value, which is equal to 1 by 2. So as we know that for J has the value plus 1 by 2, because the minus 1 by 2 is not allowed, as the negative angular momentum is not allowed. So for L is equal to 0, we have only single value of total angular momentum, that is J is equal to 1 by 2. So the component of the j. What will be the component of j in the z direction? Component of j in z direction. The component of j in z direction can be represented by jz. It can be represented by, it is equals to mj h cut. Now mj is the total, mj is the quantum number, and it is also called as the total angular momentum quantum number, and total angular momentum magnetic quantum number. So it has the value mj is can be, it varies from minus j to minus j plus 1 up to so on j minus 1 and j, that is its values varies from minus j to plus j. As all j, l and s all are quantized, as all values are quantized, so we can say that the total angular momentum all are simultaneously quantized, so they have only the specific orientations. They can have only specific orientations are possible. For the total angular momentum, only specific direction or orientations for the total angular momentum are possible, as it is the quantized both in the magnitude as well as in direction. So it has only, so it will have only the specific orientation. All orientations are not possible. Here you know that the quantized means that only the specific values, not all values. It's not continuous in its values, or rather it has only the specific value. It can attain the only certain value. So only it is, as it is the quantized both in direction as well as in the magnitude, so it can has only the specific orientation. So in the case of, here we will consider the case of one electron atom. So in the case of one electron atom, that is, you know, right, it is the hydrogen atoms. So it can has only the two possible orientation. There are only two possible orientation. Which one are these possible orientation? So j can have the orientation, either it can have the j is equals to, it can be either equals to l plus s, or either j can be equals to l minus s. So when it will be equals to the l plus s, l when its value is equals to l minus s. So j is equals to l plus s if j is greater than l, and j is l minus s if j is less than l. So this is the condition. These two are the condition which are responsible for these two orientation of total angular momentum for one electron system. So as you know that the total angular momentum is a vector quantity, as it has the both magnitude as well as it has the direction. So we can represent the j is equal to l plus s and j is equal to l minus s by we can represent it both by vector subtraction and by the rule of vector addition. So let's suppose we represent the j is equal to l plus s. So we can represent it like this one. Let's suppose this is your l vector, and here this one is the s, total s. Now we can add up, and this one is their resultant j. So it is equals to j is equal to l plus s. Similarly, we can represent the j is equal to l minus s by the vector diagram. So let's suppose this one is the total orbital minus s. We will draw the minus s like this one. So this will be their resultant j. So this is the vector diagram for J is equal to L minus S. So now we will consider how L and S interact. How L and S interact with each other to give us the total angular momentum J. So L and S, they can interact magnetically. So let's suppose we have the two conditions, how they interact when there is the magnetic field and when there is no magnetic field. So for the first condition, let's suppose we have magnetic field B is equal to 0. Here B represents the magnetic field. So when there is no externally applied magnetic field, then how the L and S interact with each other to give us the total angular momentum J. As we know that J, which is conserved both in the magnitude and direction, both in magnitude plus direction. So the effect of internal torque, there is also the internal torque which acting on the electron. So the internal torque, result of the internal torque or effect of internal torque is that there is the precession of L and S around J. Let's suppose we have the total angular momentum vector which can be represented by J. So the here the L will precess around the J and S will also precess around the J. So let's suppose this is the this vector is the L, and L will have the precession around the J. So L will precess around the J, and let's suppose this one is the S. So S will also precess around the J. It also has the precession around J. So L and S both combinedly precess around the J and gives us J is equals to L plus S. So this is the interaction of L and S, total orbital angular momentum and total spin angular momentum, when there is no magnetic field. In the absence of magnetic field, the internal torque results of the internal torque is, as a result of internal torque, the total orbital angular momentum and total spin angular momentum precess around the total angular momentum vector J. So now next we will consider what is the effect or how the L and S interact with each other when there is magnetic field. Now if B naught is equal to 0, B naught is equal to 0 here means that when external magnetic field is present, there is magnetic field. So what will happen to the orbital and plus spin angular momentum, how they will interact with each other to give us the total angular momentum J in the presence of external magnetic field. Let's suppose this one is the external magnetic field B. Now in the presence of magnetic field, the total angular momentum vector J will precess about the B. Let's suppose this one is the B and total angular momentum vector J. This one is the J. So J will precess around the B field when there is B field. And what will happen to the individual angular momenta, that is L and S. So the L and S, let's suppose this one is the L. L will continue to precess around the total angular momentum J and total spin angular momentum. And the total spin angular momentum S, spin angular momentum vector S, also continue to precess around the vector J. So in the presence of magnetic field, J precess around B field, around magnetic field. Okay, and L and S, both these precess around the J. So what will be the effect of the external magnetic field? So the precession of J, total angular momentum around the B field, it gives rise to the anomalous Zeeman effect. Anomalous Zeeman effect. Okay, and you know that the Zeeman effect is the splitting of spectral line. Splitting of spectral line in the presence of magnetic field. So whenever there is the precession of total angular momentum vector J around the B field, it gives rise to anomalous Zeeman effect, as the different orientation of J, as J is the quantized, so J has the different orientations. There are the only specific orientations, so they are slightly different in energy when they precess around the B. As a result, there will be the anomalous Zeeman effect. We can understand the total angular momentum with the help of an example. Now what is the example? Example is that it's very simple. Let's suppose we have what will be the possible orientation? What will be the possible orientation of J for J is equal to 3 by 2 and J is equal to 1 by 2. If J is equal to 3 by 2 and J is equal to 1 by 2, then what will be the total, what will be the possible orientation of total angular momentum J? As first we will discuss the case with J is equals to 3 by 2. When J is equal to 3 by 2, as we know that value of Mj, as we know that Jz is equal to Mj h cut. Mj is the quantum number, that is the total angular momentum quantum number, and its values varies from minus j to plus j. And so when j is equal to 3 by 2, the value of Mj are minus 3 by 2, minus 1 by 2, and these are the 1 by 2 and 3 by 2. So how we can plot these values? Let's suppose, and this one is the Mj is equal to minus is equal to 3 by 2, and this one is the Mj is equals to 1 by 2 when Mj is equals to minus 1 by 2, and this one is the Mj is equal to minus 3 by 2. So its value are the jz direction, it has the value minus 3 by 2 h cut, and this one is the value which is equals to minus 1 by 2 h cut, plus 3 by 2 h cut, plus 1 by 2 h cut, and this one is the minus 1 by 2 h cut, and this one is the minus 3 by 2 h cut. Now what will be the orientation of mj for j is equals to 1 by 2. For j is equal to 1 by 2, mj has the only two orientations are possible, is equal to plus 1 by 2 and minus 1 by 2. So we can plot it like this one. Mj is equals to 1 by 2, and this one is the mj is equal to minus 1 by 2. So on the jz direction, it has the value of 1 by 2 h cut, and it has the value of minus 1 by 2 h cut. So this was all about the total angular momentum vector, which is the combination of spin angular momentum and orbital angular momentum. And here we have discussed, as you know, that we have seen that the total angular momentum vector J is quantized both in magnitude in magnitude plus and direction. So it has only the specific orientation of total angular momentum vectors are possible, as here you have seen in this example that for j is equals to 3 by 2, it is proved that for j is equal to 3 by 2, it has only these specific orientation of total angular momentums are possible, and in the similarly for j is equal to 1 by 2, these only two orientations are possible. Thanks for watching. For more videos, please subscribe our channel.